In the previous video, we defined dummy variables and Bernoulli distributions. Bernoulli random variables or Bernoulli distributed random variables is a random variable that could only take two values, 0 and 1, and the probability that it takes the value 1 is called the success rate. Now, oftentimes in practice, we may observe more than one occurrences of a random variable, a Bernoulli random variable. When we observe multiple, more than one independent Bernoulli random variables, we consider them together and we call that a Bernoulli trial process. So the definition of a Bernoulli trial process, or in short, BTP, a Bernoulli trial process is a sequence of random variables, but it's a sequence that are independent. It's a sequence of independent and identically distributed and these random variables have to be Bernoulli random variables. Just to give you a more concrete idea, consider this example. So if three random variables, x1, x2, x3, are three random variables, if they are independent, and if each of them follows a Bernoulli P distribution, that they have the same distribution and the same distribution is Bernoulli P. Then when you put these three random variables together in an ordered sequence like this in the parentheses, x1, x2, x3, that is a sequence formed by these three Bernoulli random variables, then this sequence form a Bernoulli trial process with parameter n and p. And here the n is the number of elements in this sequence. In this case is 3, because there are 3 elements in this sequence. Like for a more realistic example, suppose x1 is 1 if we toss a fair coin once and get a head up, and x2 is 1 if we toss the same coin the second time and get a head up. And x3 equals 1 if we toss the same coin the third time and gets a head up in the third time. Then x1, x2, x3 form the outcome from the realizations of the Bernoulli trial process. X1, x2, x3 is the outcome from all 3 trials of tossing the same coin. So a sequence, as you can see, is an ordered collection. So this x1, x2, x3, the 3 random variables in this collection are ordered. In the Bernoulli trial process is an ordered sequence, is an ordered collection of random variables. Itself, it is a random vector. We'll talk about random vectors later on, but it's a random vector. And this random vector has distribution, and that can also be described in a table like this. So to describe the distribution of this Bernoulli trial process, we first list the number of possible values for the process. Well, because each of the x have 2 possible values, 0 and 1, then this Bernoulli trial process has 2 to the power 3 possible values. And these values can be listed as follows. All of them are 0. First two are 0, the third is 1, or 0, 1, 0, or 1, 0, 0, or 0, 1, 1, 1, 0, 1, 1, 1, 0, or 1, 1, 1. So these 8 outcomes are all the possible outcomes of this Bernoulli trial process. And we can calculate the probability of each outcome using the feature of independence, using the independence between x1, x2, and x3. So the probability that x1 equals 0, x2 equals 0, and x3 equals 0 equals the product of the probability of each of them being 0. Because by definition, x1, x2, x3 are independent Bernoulli random variables. So the probability of each of them being 0, we know it's 1 minus p because they are Bernoulli p distributed. So the product of the 3 will be 1 minus p to the power 3. And the probability that the process takes the value 0, 0, 1 can also be obtained by the same principle. So it's the probability that x1 equals 0, which is 1 minus p, times the probability that x2 equals 0, which is also 1 minus p. So you get 1 minus p times 1 minus p, 1 minus p squared, times the probability that x3 equals 1, which has probability p. So that is the probability for the second outcome. And as you can see, because the 3 variables are symmetric, they are identically distributed. So the next 2 outcomes also have the same probability. That's 1 minus p squared times p and 1 minus p squared times p. So because 0 has 2 occurrences in these 3 outcomes, in each of these 3 outcomes, therefore, the probability has the product of 1 minus p, or the product of 2 1 minus p's. And 1 has 1 occurrence, so we multiply p to this product of 2 1 minus p's. Following the same principle, we can see that each of the outcome with 2 1s and 1 0 have probability p squared, because there are 2 occurrences of 1s, which has probability p, times 1 minus p, which is the probability of each of the Bernoulli random variable, equals 0. Same thing for each of the outcomes with 2 successes and 1 failure. And the probability that all 3 are successes will be given by p to the power 3. So that's how you can figure out the distribution of a Bernoulli trial process. Based on the Bernoulli trial process, we can define a useful distribution, a distribution of a discrete random variable called the binomial distribution. So what is the binomial distribution? The binomial distribution is the distribution of the number of successes in the Bernoulli trial process. So the number of successes in the Bernoulli trial process is a binomial distribution, or follows a follows a binomial distribution. And if the Bernoulli trial process is a Bernoulli trial process in P with parameters A and P, N is the number of trials, P is the success rate, then the number of successes in this process follows a binomial NP distribution with the same N and P. For example, if the sequence x1, x2, and x3 follows a Bernoulli trial process NP, then the sum of the three random variables follows the binomial NP distribution. So why the sum? Because each of them equals 1 indicates a success, one success. Then the sum means the number of ones, which is the number of successes. So the sum of n, or in this case, the sum of 3 independent Bernoulli P random variables is a binomial 3P random variable. So here in this case, n is 3. We can call this random variable y. We define this sum to be y. Y is a binomial random variable with parameter 3 and p. We can figure out the distribution of y from the distribution of the Bernoulli trial process that we obtained on the previous page. On the previous page, we obtained that the probability that the Bernoulli process is 0, 0, 0 is 1 minus p, which has 3 occurrences to the power 3. And the probability of each of the outcome with 1 success and 2 failure is 1 minus p to the power 2 times p. And the probability that for each of the outcome with 2 successes and 1 failure is 1 minus p to the power 1 times p to the power 2. So the failure rate to the power 1, which is the number of failure, and the success rate to the power 2, which is the number of success. And the probability of having 3 successes in the process is p to the power 3. Now the value of 1 corresponding to each of the outcome for the Bernoulli trial process can be calculated by summing up the 3 numbers. So it's 0 for the first line, and 1 for the next 3 outcomes, and 2 for the next 3 outcomes, and 3 for the last outcome. Now we can compress the table to get the probability distribution of y. So y, obviously, it takes 3 possible values, 0, 1, 2, and 3. And each with probability 1 minus p to the power 3. There is only 1 outcome that has this probability. So that's the probability that y equals 0. And there are 3 outcomes for y that correspond to y equals 1. So the probability that y equals 1 is 3 times 1 minus p squared times p. Same thing for y equals 2. That's also 3 outcomes. And the probability that y equals 3 corresponds to 1 outcome, which has probability p to the power 3. So this is the distribution of binomial 3p random variable. In general, suppose that the number of trials is not 3. Let's say we consider a Bernoulli trial process with n trials, and correspondingly a binomial distribution with n trials and success rate p. How do we figure out the distribution of this more general binomial distribution? Well, first, let's define this distribution. Suppose let x1, x2 to xn be a collection of independent and identically distributed Bernoulli P random variables, then the sequence formed by these n random variables is a Bernoulli trio NP, and the sum of the random variables is the binomial NP, follows a binomial NP distribution. Before trying to figure out the probability mass function of this Bernoulli, of this binomial NP distribution, we see that it's actually not necessary to get the probability mass function first in order to get the expectation and variances. So we can get the expectation of this binomial NP distribution, let's say this is y, without getting the probability mass function first. We can use the properties of expectations and variances. So let's use first the property, the linearity property of expectation. The linearity of expectation tells us expectation of sum of random variables equals the sum of the expectations. And because we know all n random variables have the same Bernoulli P distribution, and Bernoulli P distribution has expectation P. So therefore, that's P plus P plus da 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 plus P. There are n of them. So the result is n times P. That is the expectation of the binomial random variable. And to get the variance of y, the variance of the sum of random variables in general does not equal to the sum of the variances of each of the random variable, because there might also be the covariance terms of the random variables. But these x1 to x2 to xn random variables are independent. We have learned that independence implies mean independence, and that implies linear independence, which is zero correlation. So these x variables do not have correlation between them. Therefore, the variance of the sum equals the sum of the variance. So this is because they are independent. And the variance of each of them is the variance of the Bernoulli P distribution, which remember is P times 1 minus P. So there are n of them that you are adding up. So you get n times P 1 minus P. That is the variance of the binomial NP distribution. Now, maybe, so the expectation and the variances describe some aspects of the binomial distribution, but sometimes you might need to actually know the distribution itself. So let's try also to figure out the probability mass function of the binomial distribution. First, I'm going to claim that the binomial distribution has the following probability mass function. So that's the notation for the probability mass function. And the binomial distribution, because it's the number of successes in n trials, it can only take integer values from 0 to n. Right, so let's say the probability mass function. We want to figure out the probability mass function for the point k, for y equals k. Then that is the probability that k of the n variables are ones and the rest are zero. So this statement describes what this probability mass function at k means. Right? So if k of the n random variables are ones and the rest are zero, then the number of successes is k. So that's just another way of stating the definition of the binomial distribution, binomial random variable. K of the random variables are ones and the rest are zero. That correspond to different outcomes of the Bernoulli trial process. If you look back at this n equals 3 case, k, let's say when in this case, when k equals 1, there are 3 outcomes of the Bernoulli trial process that's consistent with k equals 1. And each of these outcome has probability 1 minus p to the power n minus 1, which is 2, times p to the power 1. So as you can see, as you can infer from this simple example, the probability that y equals k has 2 components. One is the number of outcomes for the Bernoulli trial process with n successes. And the second component is the probability for each of such outcomes. So the PMF, so this probability should be the number of outcomes corresponding to the number of outcomes consistent with n successes times the probability of each of these outcomes. Let's look at the probability of each outcome consistent with this first. Each outcome that consistent with k successes and n minus k failures should have probability p to the power k times 1 minus p to the power n minus k, because p is the probability of success and there are k number of them. And 1 minus p is the probability of failure and there are n minus k number of them. So the product of k p's and n minus k 1 minus p's should be the probability of each of the outcome consistent with having n successes. And there are typically more than one occurrences of such outcome, more than one such outcomes consistent with k successes. And this number here, I write big parenthesis nk, that is the number of outcomes with n successes. What is this number? This number is read as n choose k. It is the number of ways to choose k elements from a collection of n elements. In this particular example, in the Bernoulli, in the binomial example, it is the number of ways to choose k random variables and let them to be success and let the rest be failures from n trials. So intuitively, if you think about it a little bit, you can see this is the number of distinct outcomes with k successes and n minus k failures. So that's why the probability mass function of the binomial distribution at k is this n choose k times p to the power k 1 minus p to the power n minus k. it's important to know that this n choose k is the number of ways to choose k elements from a collection of n elements. These k elements are not ordered and not repeated. So if you are choosing elements from 1 to 3, suppose you are choosing 2 elements from these 3 elements, then choosing 1 and 2 and choosing 2 and 1, these are the same way. So these are the same because ordering doesn't make the choice a different choice, okay? And that makes sense because when you are calculating the sum of the Bernoulli random variables, only the sum matters. It does not matter which ones. It only the occurrence of ones matters. It doesn't, because the occurrence is 1 in every case. It does not matter whether it's x1 equals 1, x2 equals 1, x3 equals 0, and that is the same as, so that is choosing 1 and 2. So, I'm sorry. So choosing 1 and 2 from this 1 to 3 correspond to the event that x1 equals 1, x2 equals 1, and x3 equals 0. And choosing 2 and 1 from this collection and make them successes also corresponding to the same thing, because that also makes x2 to be 1 and x1 also to be 1. And the one that is not chosen is 0. So these two are exactly the same. So n choose k is the number of ways to choose k unordered and repeated elements from a collection of n elements. Just to consider this 3-element example, how many ways are there to choose 1 element from 3? Well, clearly there are only 3 ways to choose 1 element from 3 elements. You can choose the first, you can choose the second, or you can choose the third. There are only these 3 ways. So 3 choose 1 is 3. What about 3 choose 2? 3 choose 2 is also 3, because you can look at it in a different way. Choosing 2 from 3 elements is the same as leaving 1 out from the 3 elements. Well, you can leave out 1, you can leave out 2, and you can leave out 3. These are the only 3 possibilities of leaving 1 out or choosing 2. So 3 choose 2 is also 3. So these are simple examples, but in general, what is n choose k? How do you calculate the number of ways of choosing k elements from a collection of n elements? To get the formula in general, let's consider actually a different problem, because the formula for n choose k can follow from 2 ways of doing this different problem. Consider this different problem. The different problem is as follows. We want to figure out the number of ways, how many ways there are to put k of the n numbers into k boxes. So this k is these 2 k's are the same. Okay. How to put k of the n numbers into k boxes? This is a different problem than choosing k elements from these n numbers. Because choosing k elements, we're not ordering these k elements. But putting k of the numbers into the k boxes, the numbers that you take to put in the boxes, they are ordered because the boxes are laid out in an ordered sequence. So this box 1, box 2, box 3, and box K. It's in fact easier to do this problem. There are two different ways to solve this problem, to figure out the number of ways to put K elements out of the n numbers into the K boxes. One way to do it, these two ways should yield the same answer because they are solving the same problem. If they're solving the same problem, they should give you the same solution. The first way is to fill the boxes sequentially. Let's choose a number and put in this first box. How many ways there are to choose a number and put in the first box? Well, there are n numbers total, so there are n ways to choose a number for the first box. Now the first box is filled. Let's choose a number to fill the second box. How many ways there are? How many possible numbers to choose from to fill the second box? Now there are only n-1 ways to fill the second box because you have used one number already to fill the first box. And you can keep going sequentially until you fill all the boxes. And that number you get will be the number of ways to fill the K boxes using the n numbers. And that's the first way. And the first way gives you the answer, that is n times n-1 times n-2 to n-k plus 1. Because when you are filling the last box, you are left with only n-k plus 1 numbers. And you're choosing one from these numbers, and that's n-k plus 1. That's the first way. It gives you an answer. And the second way to solve this problem is to first choose K numbers, not ordered. Choose K numbers from this n. And then throw away the rest of the numbers and just keep these K numbers. And now put these K numbers sequentially into the boxes. That also will fulfill your task. How many ways are there according to this approach? Because this approach takes two steps. One step is to choose K numbers from n. There are n choose K ways to do that. And once you have done that, you put these K chosen numbers into the K boxes. You fill each box sequentially. The first box, there are K ways to fill it. The second box, you have K minus 1 ways to fill it, and so on and so forth until you are at the last box and you are only left with one number. So there is only one way to fill the last box once you have filled the other boxes. So this second way to solve this different problem gives you this answer. And these two ways are solving the same problem. Their answers should be equal. When you set these two on the two sides of an equation, you can figure out what n choose k is. So now if you set the two answers the same, set them equal, sorry. Now you set them equal, you find n choose k is n times n minus 1 times n minus 2 times n minus k plus 1 divided by k, k minus 1, k minus 2 times 1. So and that is exactly what n choose k is. But usually people write this n choose k in a short way using the factorial notation. When you, so this k times k minus 1 times k minus 2 to 1, that is often called the k factorial. And on top, you don't get n factorial. It's not an n factorial. It's truncated somewhere. But if we fill it up, if we complete that factorial, but to keep the expression, to keep the value of the expression, we have to divide the terms that we filled on the numerator. And we find that the quantity we use to complete this factorial is also a factorial. This is also a factorial, and it is n minus k factorial. And on top, the one that we completed is n factorial. So n choose k, when written in a short way, is n factorial divided by n minus k factorial times k factorial. So that is n choose k. So therefore, that gives you the probability mass function of the binomial distribution. Okay. And to make some connection with the terms that the book defined, this problem, this different problem that we solve, the number of ways to put k of the n numbers into k boxes, that solves a permutation problem. Well, n choose k solves a combination problem. So when you choose k numbers unordered and repeated from n elements, you are choosing k combinations. So that problem solves the combination problem. Well, when you put k numbers out of n numbers into k boxes, k ordered boxes, that is a permutation problem. Each way of doing it is a permutation. All right, so that's the distribution of a binomial distribution, the distribution of a binomial random variable.